Okay, so for years now, there's been this massive, ongoing debate in the machine learning world. When it comes to generating truly high quality images and videos, do you absolutely have to use diffusion models? Or can autoregressive models actually do the heavy lifting? Well, a recent breakthrough from BAII called Emu3 has totally stepped up to challenge everything we thought we knew about this. Today, we're going to unpack exactly how Emu3 pulls this off. And honestly, we'll be looking at the future of generative AI through a completely new lens. Here's our roadmap for this explainer. We'll start by looking at the diffusion status quo, unpack the Emu3 paradigm shift, see how they finally crack the visual tokenizer, and then we'll dive right into their unified training, the CFG tricks they use, and of course, the real-world performance trade-offs. Let's get right into it. Section 1. The diffusion status quo. To really appreciate what Emu3 is doing here, we first need to set the stage and look at where the machine learning baseline stood through 2024. Until very recently, the conventional wisdom was pretty stark. Diffusion models, the engines behind Stable Diffusion, Midjourney, DALL-E 3, they were the absolute gold standard for high-end images. The whole industry was basically built on this assumption that you literally needed diffusion to get that high-fidelity, stunning image quality. On the flip side, the standard belief was that autoregressive models, which just predict data step by step, would inevitably lose way too much intricate detail. The prevailing argument went like this. If you break an image down into discrete tokens, you're going to accumulate so many errors across thousands of steps that you just end up with a blurry, messy image. It was total industry dogma. For images, you use diffusion, period.
Section 2. The Emu3 paradigm shift. So what if that entrenched industry dogma was just entirely wrong? Emu3 relies completely on something called next token prediction, or NTP. Now, this is just the standard autoregressive loss that predicts the next token in a sequence. If you have any idea how large language models like ChatGPT work, you already know this engine. They just predict the next word or token in a sentence. What Emu3 does is take this exact same, beautifully simple mechanism and apply it to visuals. The idea is, as long as the data, whether that's text, an image, or a video, can be broken down into a vocabulary of tokens, next token prediction can learn to generate it.
The researchers behind Emu3 made an incredibly bold bet here. They essentially said, a better tokenizer plus scale is all you need. They claimed you don't need these crazy complex diffusion schedules or entirely separate architectures for images. If you can just build a vastly superior visual tokenizer to perfectly translate raw pixels into tokens and then throw massive computational scale at it using standard next token loss, you can absolutely beat diffusion models at their own game.
Section 3. Cracking the visual tokenizer. Of course, the magic phrase in all of this is superior visual tokenizer. Let's dive into the actual mechanics of how Emu3 pulls this off and translates pixels into a language the model can actually read. 4096. I really want you to remember this number because it brilliantly illustrates the power of Emu3's inverse bottleneck quantizer, or IBQ2D tokenizer for short. Here's how it works. The tokenizer takes a standard 512 by 512 pixel image and applies an 8 by 8 resolution reduction. Mathematically, it squashes that massive grid of pixels into exactly 4096 discrete tokens. But, and this is absolutely crucial, it doesn't just compress it into garbage. It retains astonishing quality, hitting a 30.5 decibel reconstruction PSNR. To put that into perspective for you, Stable Diffusion's highly touted continuous latent space hits about 32 decibels. Emu3's tokenizer is remarkably close to that. Getting right up near that 32 mark is fantastic, meaning it preserves incredible detail even in a strictly tokenized format.
And hey, it doesn't stop at still images. To turn moving video into a language, the tokenizer uses spatio-temporal patches. Imagine a 4-second video clip running at 8 frames per second. That gives us 32 frames of video, right? The tokenizer applies a 4x4 reduction across the x-axis, the y-axis, and the time axis. So your 256 pixel width becomes 64, the 256 pixel height becomes 64, and those 32 frames of time become just 8. If you multiply 64 by 64 by 8, you get exactly 32,768 tokens. Just like that, 4 seconds of rich, complex, moving video is mathematically compressed into a neat, highly structured stack of integers. It's like a giant puzzle coming together. Section 4. One loss to rule them. Now that the tokenizer is cracked, the model has a unified language to work with. And this is where the elegant simplicity of Emu3 truly shines. Because text, images, and video now share the exact same vocabulary, Emu3 uses a single identical training objective for everything. Want to generate an image? The model is trained on a text caption, followed by an image tag, and then the image tokens. Want it to perceive an image and answer a question about it? Just feed it the image tokens, ask your question, and it predicts the text answer. Video generation? Same exact thing, just swap in the video tokens. The beauty here is the single loss training. The model just organically learns from the data when it's appropriate to spit out a text token versus a visual token. There are 0 separate training pipelines here. Because of this totally unified training, Emu3 actually functions as 3 distinct APIs. Emu3 Gen for creating images, Emu3 Chat for visual question answering, and Emu3 Stage 2 for video tasks. But here is the kicker, and this is wild. These aren't 3 different models. There are absolutely no task-specific heads slapped onto the architecture. It's the exact same underlying 7 billion parameter brain. It just responds differently depending on the prompt template you give it. Section 5, borrowing the CFG trick. So the training is purely autoregressive, but Emu3 actually borrows a brilliant trick from the diffusion world during inference to guarantee those high-quality outputs. To seriously boost image quality, Emu3 uses something called classifier-free guidance, or CFG. First, it generates tokens using your specific prompt. Then, it generates them all over again using an entirely empty caption. Finally, it mathematically mixes those raw predictions, the logits, using a specific guidance weight, usually somewhere between 3.0 and 7.0. By pushing the final output further away from the empty result and closer to the prompted result, the visual quality just skyrockets. Oh, and a quick note on temperature control. Keeping the generation temperature at around 0.8 prevents any weird visual artifacts or mode collapse, while bumping it to 1.0 is perfect for perception tasks. Section 6, performance and trade-offs. Look, the theory is incredibly elegant, but we really need to look at the hard data. Let's ground this excitement and objectively analyze Emu3's benchmark scores, as well as the very real computing costs. Starting with image generation on the MJHQ30K FID benchmark. Now remember, lower is better here. Emu3 scores a 5.4, which actually edges out Stable Diffusion XL's score of 5.6. This is a monumental validation of their whole thesis. A purely autoregressive next token model genuinely beating a state-of-the-art diffusion model at its own designated game of image fidelity? That's a huge deal. And the versatility here is just remarkable. Check out the VQ-A2 benchmark for image perception, where higher is better. Emu3 scores a 75.1, beating Lava 1.6, which is a highly specialized vision language model sitting at 72.4. Remember, Emu3 isn't just a generator. The exact same underlying weights that drew the picture are also better at analyzing pictures than models built specifically for analysis. No way, right? But we have to be totally objective here. There is a massive, and I mean massive, trade-off when it comes to speed. The training efficiency matches the compute needed for something like Llama 2 or Stable Diffusion 3, which is great. But generating those 4,096 tokens one by one, autoregressively, that takes Emu3 about 2 full minutes to create a single 512 by 512 image. Compare that to Stable Diffusion XL, which takes, 2 to 5 seconds? So while that unified training is deeply elegant, actually running the model to generate images at inference time is significantly slower and highly compute-intensive. But even with that speed bump at inference, the deep conceptual contribution here is what has the entire research community buzzing. Emu3 proves that these complex Frankenstein-style pipelines might soon be a thing of the past. You might not need separate text encoders, separate diffusion schedulers, and separate VAEs all bolted together anymore. The future of AI might honestly just be one transformer, one high-quality tokenizer per modality, and scale, the whole shebang in one clean package. Which leaves us with a pretty fascinating final thought to chew on. If a single next token predictor can truly master text, images, and video with just one architecture, are highly specialized AI models already obsolete? It's an incredible thing to ponder as we watch this technology evolve right before our eyes. Thanks for joining me for this explainer on Emu3. Keep learning, and I'll catch you in the next one.